We're surrounded by algorithms making huge decisions about our lives every single day. But what happens when the math, the stuff that's supposed to be totally impartial, actually learns to be unfair? Let's dive in.
We all have this deep-seated trust in math, right? We think of it as pure logic, a world of clean lines, right and wrong answers, completely separate from the messy, tangled biases of the human mind.
And yet, you hear these stories all the time. Biased algorithms deciding who gets a loan, who gets a job, even playing a role in the justice system. So, what gives? This is the central puzzle we're going to unpack. How does something so objective lead to such biased outcomes?
To get to the bottom of it, we first have to understand the algorithm's fuel, and that's data. And as you're about to see, data can be, it can be incredibly deceptive.
Okay, so take a look at this chart. It shows the number of murders committed with firearms down in Florida. See that big marker for 2005? That's when the Stand Your Ground law was passed.
So, just looking at that trend line after 2005, what's your first impression? It kind of looks like the law worked, right? Like the number of deaths went down. But here's the trick. Look closer at the y-axis. On the left, the numbers are inverted. 0 is at the top. The number of deaths didn't go down at all. It actually shot way up. It's a classic, really powerful example of how data can be presented to just flat out mislead you.
And this isn't some rare one-off trick. It is everywhere. On the left, you've got a chart about gas prices with a skewed axis to make a tiny increase look huge. And on the right, a pie chart where the numbers add up to 128%. Come on, if the data you feed an algorithm is this flawed, what do you expect the results to be?
So far, we've seen how people can intentionally twist data. But what happens when that bias isn't a deliberate trick? What if it's unintentionally baked right into the code itself?
See, this is where the stakes get incredibly high. We're not just talking about a confusing graphic in the news anymore. We're talking about automated systems that can decide whether you get a job, a loan, or even your freedom.
Let's get into a critical, real-world case, the Compass algorithm. This is a risk assessment tool that's been used by judges in the United States to try and predict the likelihood that a defendant will commit another crime.
A really groundbreaking investigation by ProPublica dug into this algorithm's performance, and what they found was, it was deeply troubling. The errors the algorithm was making weren't random. They weren't distributed equally at all.
If you just look at all of its predictions, the Compass algorithm was correct about 61% of the time. Now that's better than a coin flip, which might sound okay on the surface.
But, and this is the crucial part, despite that overall accuracy, the algorithm was almost twice as likely to falsely flag black defendants as future criminals compared to white defendants. So, the type of error it made was systematically biased. The big question is, why?
So let's investigate the root causes. Why do these algorithms, which are built on pure logic, end up reflecting and even amplifying our worst biases? It's time to hunt for the ghosts in the machine. The first ghost is what we call historical bias. Think about it. Machine learning models learn by finding patterns in data. So if you feed it data from a world full of historical prejudice, the machine is just going to learn that prejudice as a valid pattern to follow.
Right. Imagine training an AI to approve mortgages using decades of decisions made by human loan officers. If those officers had biases, conscious or not, the AI will learn those exact same patterns and just replicate them, only now it has the false authority of being an objective machine.
The second ghost is even more insidious. It's the feedback loop. This is where an algorithm's predictions don't just reflect reality, they actually start to shape reality in a way that confirms the original bias. Predictive policing is a perfect example of this. So first, an algorithm flags a community as high risk. Because of that prediction, more police are sent there. Well, naturally, with more police on the streets, you're going to get more arrests, often for minor things. This new arrest data then gets fed back into the system, which then says, see, I was right, this area has a high crime rate. It becomes a self-fulfilling prophecy, powered by data. And finally, there's sample size disparity. Basically, algorithms are hungry for data. They're most accurate when they have tons and tons of examples to learn from. So if a minority group is underrepresented in the training data, the model just won't be as good at making accurate predictions for individuals from that group. Simple as that. So, the problems are clear, right? Historical data, feedback loops, data disparities. The obvious next question is, well, how do we fix it?
And this is where it turns out that defining fairness in mathematical terms is incredibly difficult. See, fairness isn't just one single concept. Researchers have developed dozens of mathematical definitions for it. Each one tries to capture a different piece of what it means to be fair, from making sure different groups get approved at the same rate to making sure the error rates are the same for everybody.
And these definitions can be in direct conflict with each other. For example, group fairness looks at average outcomes for whole populations. But individual fairness argues that two people who are similar based on relevant factors should get the same outcome, period. You can see how those two very noble goals might not always be compatible.
And this is the core of the problem. There's a famous result in this field that proved that, except in some very specific situations, it is mathematically impossible for a single algorithm to satisfy several of the most common definitions of fairness at the same time. There is no simple fairness button you can press. Choosing one definition often means you have to sacrifice another.
This brings us to the final and maybe the most important part of all this. If the map itself forces us to make these trade-offs, then the problem is no longer just a technical one. It's a societal one.
This is the question we really have to grapple with. We can optimize an algorithm for one specific definition of fairness, making it mathematically fair by that one standard. But if that system still leads to outcomes that we, as people, see as deeply unjust, then what does that mathematical fairness even mean? It's a choice not about code, but about our values, and that's a decision that we have to make, not the machine.